lecture of our colleague João Firmo. Congratulations for that. I've already congratulated you for winning that contest and to be assistant professor of the Department of Civil Engineering, Architecture, and Environment. So we have a lot of people professors relying, but fortunately there are a few people that new professors that have the opportunity to start their career here at the department. And João Firmo was our most recent acquisition as a professor here. So this inaugural letter, the intention is that it can give us a big overview of what he intends to do regarding the research. So he already has a very long experience as a researcher in the department, so it will be an easy inaugural lecture for you to say what you are going to do in the future, probably in the line of things that we are studying, and probably some new ones because now you are different scientific area, so maybe you have new ideas. So after this inaugural these few words by me, we are so I will ask questions for all these of the second to say a few words as well.
So good morning everyone, and welcome to the inaugural lecture of Professor João Firmo, who is newest professor about scientific area, which is structural mechanical structures. It is with a great pleasure that we welcome João Firmo to our scientific area. And there will be some notes not to forget. João Firmo has distinguished in several topics, namely structural fire engineering, fire behaviour concrete structures, application of fiber reinforcement polymers, FRPs, and strengthening of concrete structures using FRP systems. We are confident that with the expertise of João Firmo, we can strengthen our scientific area, and with the dynamism of João Firmo, we can get new students for the master and for the course of civil engineering. So, in the name of the scientific area, in my name, I wish a great success for João Firmo, and we are confident with his abilities to strengthen our scientific area. Thank you.
Professor Eduardo is not here in person today, so he sent us a video. A small Professor Eduardo is not here in person today, so I think concrete is the most building. Hello, everyone. Like begin my brief presentation by part of this excellent initiative, and by formally welcoming our new colleague João Firmo. As head of the structural group, I'd like to emphasize that concrete is the most widely used building material globally. As a result, concrete structures play a vital role in people's lives and by forming bonds. Our new colleague João, given that I as head of the structural group, highly emphasize that concrete national civil engineering school must have a solid structure. As a result, concrete structures will enable for education lives and by forming bonds. Research in college and also from the structural
show you in about 35 minutes a brief summary of what was my path here at CERIS. Can I continue? Okay. So the title of this presentation is the show in about 35 minutes. In about 35 minutes, summary what was my summary what was my CERIS. Let's wait here a bit to solve this delay. I think it's related to Can I continue? Yeah. So, as I was saying, my presentation entitles 5 behavior of concrete structures incorporating fiber, reinforced polymer, FRPs, systems, and materials. And I decided to show a brief summary of the studies that I developed during my PhD and some topics that I proceed investigating here at CERIS. The presentation is divided in 3 main parts. So first, I'd like to show you a brief summary of my academic and professional path. It's quite straightforward. The main part of this presentation describes the research activities that I developed here at CERIS, and I decided to show you the 5 behavior of 2 types of concrete structures. So concrete structures straight with CFRP systems, and so existing concrete structures, and new concrete structures that are internally reinforced with GFRP bars. And a third and last topic about concrete columns reinforced with GFRP bars. And I will conclude mentioning what are the teaching activities that I'm now currently involved with, and present the current research topics that I'm currently working, and some thoughts about future research topics that I would like to use. Some personal facts. So I was born in Cascais. I'm now 37 years old. I'm married. I'm father of 2 boys, Francisco and Pedro, with 6 and 5 months old. And my base education level was done in Sintra, where I currently live. My education university was done here in Technical. I got my master's degree in civil engineering in the specialization field of structures in 2010. And then I proceed my PhD studies also here at IST, which I concluded in 2015. In both cases, I was supervised by Professor João in the case of my master thesis, Professor Paulo França was still here at IST. And my PhD thesis, as I said, was supervised by Professor João and also by Dr. Mário Arruda. And during my PhD studies, I spent a few months abroad at the University of Edinburgh. So my PhD studies, they were funded by individual FCT scholarship. Then I applied and succeeded to an individual postdoc FCT scholarship, which was hosted by CERIS and ISIS. At the middle of this 6-year scholarship, I was hired by EIB and hosted by CERIS as a junior researcher. At the middle of this 6-year contract, I applied for individual contract from FCT as auxiliary researcher, and very recently I was hired as assistant professor at IST. So after getting my PhD degree, I've been participating in teaching activities here at IST, mostly in courses integrated in the master program in civil engineering, but also with some participation in courses from the PhD degree in civil engineering. I've been also involved in consultancy and advanced training activities through Fundec. This slide just show you some examples. On the left, some pictures of a work that I was involved with collaboration of Mário Garrido, where we helped a company developing a fire protection system for a anchor head of a cable stay bridge, and we also did some tests here at IST to validate this system that we helped develop. Here is a picture of the anchor head protected, and this is a look of the system after the fire resistance test. On the right, some examples of the training activities where I've been involved. And here I was responsible for a module of one course regarding the design of concrete structures with FRP materials and systems. So, moving on to the second part of this lecture. But first, I would like to acknowledge to all the people that made this research possible, and especially to the PhD students that I was lucky enough to supervise across these years. So special thanks, Wallace, Inês, Pietro, Adriana, and Elisa. This is truly a teamwork. So the research that I'm about to show you is the results of our work. Special thanks to Mario Huda, who has been supporting all the numerical studies that I've been involved with during the last years. Also, a special thanks to the laboratory technicians that made all the experimental tests possible. And last but not least, my scientific supervisor, but more than that, my mentor and the role model, Professor João Correia, since the first time that we started working together back in 2009. So it has been truly been a teamwork, and things that I'm about to show is are the results of this teamwork. So now a brief overview of the research path and the main topics that I've been working on. So in terms of nature of the research, I think I can say that mostly of my research is experimental, but complemented has also with numerical simulations. And I've been working especially on two main topics that I organized here with two representative pictures. So I've been working on existing structures, concrete structures strengthened with CFRP systems, new concrete structures internally reinforced with FRP bars, and all FRP and sandwich structures. And across all these three domains, I've been focusing mostly on the behavior of these structures under elevated temperatures and fire. But for the topic on the middle, I've been also paid significant attention to concrete columns reinforced with FRP bars, but in this case, studying the behavior of those columns at the ambient temperatures condition. So the first topic, my first steps in the research at CERIS started in 2010 with the development of my master dissertation in civil engineering on the topic regarding fire behavior of RC structures strengthened CFRP systems. That I continue researching during my PhD, and then during the postdoc phase of my career, supervising one PhD student and three master students developing their dissertations related with this topic. And this research was funded by three research projects. Later in 2016, I started working on concrete structures internally reinforced with GFRP bars. And this was part of my postdoctoral program that I applied to FCT, but also related and anchored in the supervision of two PhD students and 6 master students who developed their research in this topic. This research was funded by an FCT project and is being funded by CERIS in an ongoing internal project. The last topic I started working on in 2019, the 5 behavior of all FRP structures, and this research was anchored on the supervision of 2 PhD theses and the contribution of 3 master students, and it was funded also by 1 FCT project. So now, describing very briefly some of the highlights of the research on the 3 topics that I mentioned before, and starting with the 5 behavioral RCP structures, strengthening with CFRP system, and to give you a brief context of and motivation of this topic. These systems have been successfully used over the last 3 decades to strengthen existing RC structures, and there is a significant number of applications worldwide where these systems are being applied for concrete confinement, flexural, and shear strengthening. Although they behave very well, and then they are now being designed worldwide, there is also a very well-known problem of this system, which is the fire behavior. And these systems, they do not present a very good fire behavior because both materials involved in this system, the FRP material and the polymeric adhesive, which is used to bond the FRP to the concrete surface, both materials are highly affected by temperature. So when heated, these materials undergo a glass transition process, and during this process, their properties are highly affected. Here on this picture, on this corner, we can see the reduction of the material properties of both the FRP materials and the adhesive. And we also can see that the adhesive material is much more affected by temperature than the FRP itself. So, as the adhesive is responsible for the connection of the FRP material to the concrete surface, the bond behavior is highly affected. So, when we start investigating this topic, the research on this topic was relatively scarce, and the design codes that were at that time available for the design of these systems, they also recognized the problem, but they did not provide a time solution for it. So a designer that faced that wanted to check the safety verification of these systems with fire, there was no information available. So this was the starting point of this study. And the first step was done in my master dissertation in 2010, where we did some preliminary tests on this topic, and the conclusions were interesting at that time. So we did some fire resistance tests, where we tested beams, okay, strengthening flexure with CFRP systems, and we conclude that if we protect only the anchorage zones of the system, the CFRP system were able to withstand load and to contribute for the flexural strengthening, even after the bond of the CFRP to the concrete was destroyed at the central point. So protecting the anchorage insulation of the system, we were able to explore the contribution of the system by a cable behavior, as you can see. And with this system, only providing insulation at the anchorage, we observed that we were able to attain 23 minutes of fire resistance, which, by the way, is not enough for typical building requirements, but we also confirmed that combining the insulation of the anchorage zones with additional insulation at the central part of the system, we were able to attain fire resistance times that fulfill typical building applications requirements. And we also confirm that or conclude that probably the glass transition temperature of the adhesive could be considered as a critical temperature to be used on the design and safety verifications of this system when related to fire safety. So, the first step was my master thesis. Then we proceed this investigation during my PhD thesis. where we decided to investigate in further depth this topic. And for that, we divided the research into two main parts. So first, we focused on a deep understanding of the bond behavior of CFRP concrete interaction at elevated temperatures. And for that, we designed an extensive experimental campaign. At that time, those tests were performed in LNEC, and this was also complemented by numerical studies. Then, the second part of the study was at a different scale of analysis. So we moved to the structural member scale analysis, where we tested beams and slabs under fire, and we combined the fire resistance tests with numerical analysis. Regarding the first part, so the study about the bond behavior of the CFRP to the concrete, we decided to investigate the influence of different parameters that I will not describe in detail here, but we studied the influence of different application techniques. So EBR, which stands for externally bonded reinforcement, where the CFRP is bonded at the surface. And we also investigated NSM, where the CFRP material is bonded inside grooves that are open in the concrete cover. And we investigated the influence of different parameters, different configurations, and different materials. And with this experimental campaign, we were able to obtain new data at that time to the literature, providing results about the bond strain reduction with temperature for all these configurations of striking systems, also providing new data regarding the stress distributions along the bonded length and how these stress distributions change with temperatures and how they change across the different materials. And using all these new data at that time in the literature, we were able to calibrate bond slip models, also new at that time to the literature. And these bond slip curves were very useful and important to be used on numerical simulation analysis of concrete members strengthening these systems under fire. With these bond laws that were calibrated, we were able to explicitly simulate the debonding of the CFRP system during fire. And this is a significant advance in the literature at that time. But those numerical models, they needed to be calibrated with experimental data. So we also did some fire resistance tests to compare with numerical results. And here is the fire resistance test setup that we have here at CERIS laboratories, where we use a furnace that follows a typical standard fire curve. This furnace applies a heating curves to the bottom part of the member that is being tested, and the member is being subjected to the fire action and simultaneously subject to a constant load. In this case, we adopted a 4-point payment configuration, simulating a typical load scenario that is expected in a fire load combination. So these were the tests that were performed at that time, and some pictures exemplifying what we observed. So when the CFRP system was left unprotected, we confirmed that, well, they are very susceptible to fire action. Here you can see that the system debonded only after 2 minutes of fire exposure when left unprotected. Applying the fire protection system only to the anchorage zones, we can see that we were able to explore that cable behavior that I mentioned before. And with this, we extended the fire resistance up to 15 minutes. Again, not enough for typical building requirements, but combining these thicker insulation zones with thinner insulation applied at the anchor zones, we then were able to extend the fire resistance of the striking system, which was our goal initially. And well, this plot with a lot of numbers summarize the fire resistance times that we were able to achieve. The numbers above these bars, we can see that exceeded the typical fire resistance times required for buildings in terms of minutes, which, by the way, can be defined as 30 minutes, 60 minutes, and 90 minutes typically. So with the different configurations of fire protection and materials that we tested, we were able to find a solution for that problem that I described before. Well, but designers don't have time usually to make such complicated numerical simulations as those I mentioned before. Usually don't have time and means to perform fire resistance tests as I did in my PhD thesis. So at the end of my PhD thesis, our goal was to try to draft and to propose a simplified design methodology for the design of fire protection. And we propose a very simple methodology, which was based on exploring that cable behavior that I showed you before, and the methodology can be defined in two main parts, let's say. For the design, the thickness of the firing protection for the anchored zones, this thicker layer of protection is defined based on critical temperatures that we also defined during my PhD, and the thin layer of protection that should be designed for the central part of the system should be able to avoid the tensile failure of the FRP material and to design the thickness at that part. The material should be designed to avoid that a certain limit temperature is not exceeded to avoid that tensile failure of the FRP that I mentioned before. So in terms of main contributions of this research, well, as I mentioned, well, a significant new data new data to literature was provided at that time regarding the CFRP concurrent interaction, and also regarding the mechanical contribution of the CFRP during fire, which was one of the main topics that was not fully understood in the literature. And one of the main contributions was that design methodology that I just mentioned to protect the systems and to be able to fulfill typical building requirements. And at the end, we were really happy to see that this research was recognized in one of the most adopted design codes for these systems that mention our study and that strategy where we should apply thicker insulation at the anchorage. That the design code mentioned our study as one of the possible reference to solve the problem related to the fire resistance of CFRP systems. And we were also happy to see that our publications have been used on real-world applications. And here I show you a picture of a real-world application here in Portugal, where fire protection was designed, and I was in direct contact with the designer of the system, and he actually used our results and our publications to select the fire protection of that complete slab that was threatening CFRP systems. So that was the study that I involved during my PhD, but that topic was further investigating during my postdoctoral research in the framework of my postdoctoral FCT scholarship, but also in the framework of an FCT project which funded that research after my PhD, and in the framework and highly anchored on the PhD thesis of Adriana Spear. And also receiving the contribution of master students that developed their master dissertations in these topics. So the objectives after my PhD were to consolidate the research that I developed previously, So making improvements on the experimental and numerical methods that were used during my PhD, but also expanding that knowledge that was attained during my PhD to other variants and CFRP strengthening. And we also establish collaboration with associated industry and with other institutions to develop or to proceed with the investigation on this topic. So just to show you some examples of the improvements that we did on this topic, and here I show you one of the improvements that we did on the numerical, on the experimental methods that we used to characterize the bone behavior of the CFRP systems to concrete at elevated temperature. So during my PhD, here at Technic, we did not have the experimental capabilities to test or to characterize this behavior. But then during my postdoctoral research, we managed to find the means to do these tests here. So we developed these tests setup that allow us to complete in a more detailed way the experimental results and knowledge that we have previously acquired during my PhD. We were also able to develop a numerical tool that use the experimental data from the bone tests to calibrate local bone slip loss in a much more automatic and optimized way than the way I did in my PhD. So this was also an additional development on this topic. And we also assessed the fire behavior of different variants of CFRP strengthening system. Here I showed one of these systems that we also assessed, a create system, which is basically anchoring the CFRP laminates into holes that are drilled at the anchored zones of the CFRP system, so close to the supports, so providing a better anchorage capacity to the CFRP system. So we assessed the fire behavior of the system, and for that we designed a new experimental campaign where we directly compare the fire behavior of the systems, also with the one that I mentioned before, the NSM, the CFRP laminates bonded inside the concrete cover, and we compare with the traditional technique where the CFRP are bonded at the surface. Well, and the main conclusions of this study was that, well, both the create system and the NSM system, they behave much better under fire than the EBR traditional system, and using that methodology for fire protection that I mentioned before, we again were able to solve and to attain fire resistance times that fulfill typical building applications for building requirements for typical applications buildings. And finally, we also investigated the fire behavior of RC beams strengthened in shear with the ETS method, so embedded through the section method, where the strengthened material is bonded inside holes that are drilled at the middle of the cross section of the concrete member. And for that, we developed a new test setup and complemented with numerical modeling, and we conclude that, well, when unprotected, these systems are relatively susceptible to fire. So fire resistance times are relatively low when these systems are left protected, but we are also able to provide some solutions to increase those fire resistance. So this is only one slide summarizing this study, but this research, including the development of the test setup, the calibration of numerical models, it took more than 2 years. So moving on to the next topic, so fire behavior of new concrete structures internal reinforced with GFRP bars. And this study was developed in the framework of in the framework of my postdoctoral research program that I submitted to FCT. It was funded by an FCT project and anchored by Inês Rosa PhD thesis, and also with the contributions of 6 master dissertations. And we are able to, in the framework of this research, establish very relevant contributions to associated industries and especially world recognized producers of these bars. So to give you a brief context and motivation of this study, applications of GFRP bars as an alternative to conventional steel bars, the applications that are being increasing worldwide. We now have a significant number of applications where the durability of conventional steel reinforced concrete would be a problem. So this is an alternative to stainless steel reinforcement, and the increasing number of applications is due to, for one side, the reduction of the prices of these bars, but also due to the technological maturity of these materials and, of course, the knowledge that have been produced. So the advantages of these technologies are very well known. So these FRP bars, they are very light. They present a very high strength, but the main advantage is that they do not corrode. Okay. However, they present a brittle behavior. The elastic models, and especially when we are dealing with GFRP, so glass fiber reinforced polymer bars, the models is relatively low when compared to conventional steel. Bends are possible, but they are still made on factory. And the problem, one of the biggest problems of this technology was the fire behavior, which was our main focus on this research. And in fact, the research community also recognized that problem, not only because the material FRP degrades very fastly with temperature, but also the bond of the FRP bar to the concrete is also highly affected by temperature. And codes that were available at that time, they recognize the problem, but they do not provide very concrete solutions, or they provide very conservative recommendations for designers. One of these recommendations that I would like to mention is the one that was provided by the Canadian Code that said that to have concrete member reinforced with GFRP bars with 60 minutes of fire resistance, we should adopt a minimum concrete cover of 60 millimeters. Well, which is for FRP bar, whose the main advantage is not being susceptible to corrosion. It's a non-rational use of these bars, because if you are adopting a very high concrete cover to solve the fire issue, we are not taking advantage of the high durability of this material. So when we start studying this problem, this was the context. So we try to provide some answers and new solutions to this problem. And for that, we designed a research campaign that involved different scales of analysis. So at the material level, we first start characterizing the GFRP bars at elevated temperatures, so determining the tensile strain, the elastic models at elevated temperatures. Then we move to the scale of the connection between the GFRP bars and concrete at elevated temperatures. And then at a higher, different scale of analysis, we move to the fire behavior of concrete slab strips reinforced with these bars. And we established a collaboration with FRP producers that provide us different types of GFRP bars with these different surface finishes and also with different geometries. And we assessed the influence of all these parameters. So on the first scale of analysis, we were able to quantify the degradation of the tensile strength in elastic modulus of the different types of GFRP bars, which is a basic material property that we needed to proceed with this investigation. But the results that were available at that time in the literature, they were very scarce. And although it seems to be a simple test, it's quite challenging, and we provide very new data to the literature on this topic. Then we move to the bond behavior of these bars to concrete at elevated temperature, where we did direct pull-out tests with different bar configurations. We also combined experimental study with numerical simulations, and we were able to quantify the degradation of the bond strength of different types of bars with temperature, and also to provide, using parametric studies, numerical parametric studies, recommendations for the developed length of these bars as function of temperature and for different geometries. Okay. Then at the different scale of analysis, we proceed with the fire resistance test of concrete slabs using a test setup similar to the one I showed you before, where we adopted a very thin concrete cover, so much thinner concrete cover than the one recommended by the Canadian code. Okay, so we wanted to demonstrate that it would be possible to adopt very thin concrete covers for these bars and still having a good fire resistance, and we combine the experimental campaign with numerical simulations. On the experimental campaign, as I told you before, we adopted concrete covers of only 25 millimeters, and using or adopting this thin concrete cover, but guaranteeing that the anchors of the bars were kept cold during fire, we were able to attain significant fire resistance, so above 2 hours. Okay, and we also investigated the influence of lap splices of the rebars, where we intentionally introduced lap splices at the fire exposed area to promote bond failure of the bars and to investigate that the influence of that bond failure to the fire resistance of the overall member. And we conclude that with straight lap splices, the fire resistance was, well, as expected, very low, below 30 minutes, but using bent end lap splices, we were able to extend the fire resistance quite significantly. So with the bent ends of these bars at the end of the lap splices, we were able to explore not only the mechanical anchorage provided by this band, but also due to the fact that the top part of this bar is anchored at the cooler region of the concrete parts. And here are some pictures of the fire of the slabs after the tests. With continual reinforcement, the slabs failed due to potential failure of the rebars and attention, whereas with the spliced bars, failure occurred as expected due to rebar slippage inside the concrete. So at the end of these studies, we provided, I think, significant contributions, not only with the wealth of experimental data that were new at that time to literature, but also with the bond slip laws that are needed to simulate these complex problems. And at the end, we were able to draft fire design recommendations and provisions regarding the concrete cover thickness and the position of and geometry of the anchor joints and lap splices, and these drafts of fire design provisions can be considered in updated versions of design codes on this topic. So, moving on to the last topic that I would like to show you today, which is concrete columns reinforced with GFRP bars. This study was developed in the framework of Wallace PhD thesis, and we also collaborate with LMEC on this study, where we provide some of the experimental tests, and we also collaborate with one GFRP bar producer. And the motivation of this study was, well, not very good, let's say, because most codes for the design of concrete structures with GFRP bars, they do not recommend the use of these bars on concrete columns, especially those that are subjected to lateral loading. So in seismic areas, the code says that please do not use these bars. These FRP bars, they are inelastic to failure. Columns, they present mostly a brittle failure. So this was the starting point. And our goal was try to assess if there is any possibility to have any pseudo-ductility or any dissipation capacity in concrete columns reinforced with this bond. So this was the answer that we are trying first to understand and then try to answer and provide solutions. So, and for that we designed an experimental study and numerical combined with a numerical study, where we tested real scale concrete columns reinforced with GFRP bars, subjected to axial loading, tests that we performed at LNC, and concrete columns and the corresponding footing system that we test under constant axial load and subjected to monotonic lateral loading or to cyclic lateral load. Some examples of the rebars configuration that we adopted. So of course we also test reference steel reinforced concrete column. All FRP concrete columns with longitudinal GFRP bars and also with GFRP closed GFRP ties, okay, that were specially manufactured by the FRP producer. And we also assessed the possibility of taking advantage of the combination of longitudinal GFRP bars with stainless steel bars. And the goal was here to assess if we could improve the energy dissipation capacity by exploring the yielding stage of the stainless steel bars, but still maintaining the high durability of the system. And for that, we developed experimental tests here at CERIS laboratories. So the columns and the footing was pre-stressed against the strong floor of the laboratory. Okay, we found we designed a test setup that were able to maintain a constant load on the concrete column while lateral displacement was applied to the columns, either monotonic or cyclic. And for the cyclic loading, we adopted the typical loading protocol with increasing amplitudes of lateral displacements. These are the main conclusions that we obtained on this study. So we confirm that we can design concrete columns with GFRP bars with similar lateral deformation and load capacity of equivalent steel reinforced concrete. Although we need for that to adopt much higher area of GFRP rebars as a result of the lower elastic model of the bars. We also confirm that the lower ductility of and energy dissipation capacity of the GFRP RC columns, but we also show that this low ductility can be improved if we increase the deformation capacity of the concrete under compression, and we can do this by improving the confinement. And regarding the combination of longitudinal GFRP bars with stainless steel bars, we confirm that the concept can work. So we confirm that we can actually increase the energy dissipation capacity by combining or by introducing stainless steel rebars combined with the GFRP ones. But for that, we need two main conditions. So we need to provide appropriate confinement for the GFRP, for the concrete under compression, and we need to adopt a stainless steel bar that has a relatively low equivalent yielding strength, so that we can explore the yielding stage of these bars before the GFRP bars fail. Typically, they fail under compression on this application. So now, just to finalize my lecture, I would like to mention what are the teaching activities that I'm currently involved in. On the first semester, I'm teaching concrete structures 1. Then on the period 2, I will start teaching rehabilitation and strengthening of structures. Period 3, I will be teaching concrete structures 3. And on period 4, I will be teaching composites for civil engineering structures, and I will also have some contributions on other 2 courses. And one thing that I would like to be involved with, and of course this still needs to be discussed with the scientific area, would be the implementation of experimental teaching methods that I recognize it's very challenging at this stage, but I think it would be a good methodology to attract more students for the scientific area of structures. In terms of research topics, I'm currently working on the 5 behavior of precast concrete buildings in the framework of ongoing PRR project. I'm also still working on the 5 behavior of concrete structures internally reinforced with GFRP bars, but now using thermoplastic bars in the framework of ongoing research projects here at CERIS. I would like to continue working on the behavior of concrete structures reinforced with GFRP bars under cyclic and seismic actions. So following that study that I showed you before on the columns, but now focusing on the connection between beams in columns and to address how the ductility and energy dissipation capacity can be promoted. I would also like to start working on the 5 behavior of concrete structures straight with FRCM or tear-around systems. So these systems, they are an alternative to FRP systems. The use of this system is increasing worldwide. Their behavior at ambient temperature is very good, but their 5 behavior is still largely unknown. So using the knowledge that and the experimental and numerical capabilities that we have in CERIS, I think that we will be able to provide significant contributions on this topic. And the last topic that I'm trying to get the funding to start working on is the both earthquake 5 behavior of concrete structures straight with advanced systems. And the motivation for this topic, I think it's relatively easy to explain. So the number of fires that happen after an earthquake, the number of fires is significant. And the numbers are very well known. And also the consequences. For example, here I show you an earthquake that happened early this year in Japan. So the buildings were able to withstand the seismic action, but here you can see the damage after a fire that occurred after that earthquake. Okay, so the challenge that I'd like to contribute to solve this? Can we design a tracking system to improve the resilience of concrete buildings for the seismic action, but guaranteeing at the same time that we will withstand the effects of a fire after an earthquake? So that's a question that I'd like to answer in the near future. And I have no conclusions yet for this first class, because this is just the beginning of a new journey of ISP. So thank you very much for your attention. I'm available to answer any questions you may have.
We have some time for questions. Present one.
Just give some words on that lesson. I'm about to leave because I have to be examined in less than half an hour, but just to mention and like all this way to today, and it's a pleasure that you are finally getting a permanent position in technique. You know that I'm from seismic behavior, so I relate it all the time. Your conclusions, your studies, always thinking about the seismic behavior of structures. And for instance, whenever you talk about GFRP bars, before you talk about the last experimental campaign for columns, I was thinking how to use this. You are talking basically to the beams and to the slabs, to use this. How to use this for in structures in seismic areas? Because you only mentioned this problem of fragile behavior of the bars, the FRP bars, only in the columns. But even though, my question is, whenever you think about a solution to protect to the fire these steel elements, to this GFRP elements, I mean, moving to steel, have you ever think about the problem of having mass and somehow get our structures more vulnerable? We talk about Canadian suggests 6 centimeters of cover for the bars, right? And you are working or studying for 2.5 centimeters. Even though, have you ever think about using light concrete or other solutions that will not increase so much the mass?
The mass to improve the seismic behavior.
Yeah, because whenever you are increasing the mass, you are increasing the inertial forces and you are increasing the effects of you are improving the fire protection, you are increasing probably the demanding that is in this system. So there's just some notes that keep it in mind, because one of the topics is not for fire, it is by seismic and for the behavior of node, which is really very important for existing structures. But I think try always for structures in seismic areas not to increase too much, as less as possible, the mass that the structure is in. Just
Thanks for your comments and nice words. Using lightweight concrete can be a solution, yes. But I think there are also other possibilities, because as the GFRP bars, they are very durable. We can have different types of concrete, and we can also, I think we also need to adapt the geometry of our concrete structures for this new type of material. So I think we should try to think out of the box and try to think on different geometries and combine different materials. Using lightweight concrete could be one of those ways. But well, I think there is still a lot to investigate in this area, so that's why it's one of the areas that I would like to be involved in the near future. So, yeah, for the comments, I think they are very nice, and I will consider that on this. Yeah.
Just one question. Congratulations for the lecture. It is in line with what you know from you and from your research. I have a question. We have nowadays different error codes for different types of materials, but we don't have yet error code for this type of materials. What can you say about the code? And connected to this question, you mentioned, for instance, you have columns, cutting columns with the steel bars and the GFRP bars. this type of materials have different end models. So for the design, I think it's not very easy, and we have some problems of the cracks of concrete because the, let's say, the formation, the elevation of these materials, and for what we teach to students, the hypothesis of Bernoulli with plain sections, it will be, maybe it's not applied in this case. So what you can say about this and about the, let's say, the future code. I think you are involved in this future penal code, but what you can say?
Yes, I'm involved in the, thank you for your question. I'm involved in the commissions that are preparing the future version of the Eurocode. And well, the updated version of the Eurocode 2, it will include an annex that addresses the design of concrete structures with FRP bars. But it will be still informative. So it's not mandatory, it's not law. Okay? So designers can choose if they design structure following that annex or a different code. Regarding the elongation and the what you mentioned about cracking, yes, it's a problem, and that's why usually the design of these elements is governed by serviceability limit states conditions. So, for example, normal 12 to design a concrete beam with this type of bars, and this design can be governed by checking concrete openings or deflections. But it can be solved. Of course, the end result is adopting a much higher area of GFRP bars than that we would need with an equivalent concrete member reinforced conventional steel bars. But that's a way to solve it, and we can solve it.
Also, I have a question. It's about the economics of these solutions. Because there are some advantages and disadvantages. But in the end, if you can use steel, is there any economic advantage to replace steel for rebars, or you cannot tell about that?
Yes, we can. Of course, we still need to investigate the topic of life cycle analysis of these solutions. The initial costs are typically higher than conventional steel, but if we compare with the stainless steel solutions, which I think is the comparable solution, the prices of GFRP bars are now lower than stainless steel. However, if we consider the entire life cycle of structure, including maintenance costs and also the environmental costs at the end of life cycle, there is some studies that show that these solutions they are better than conventional solutions with steel reinforcement. So we can reduce maintenance costs, and we also, in some cases, we can actually avoid the demolition and reconstruction of a new structure. So there are some preliminary studies that are showing if we consider the entire life cycle of a structure, these solutions can be good.
Great, thank you very much. I suppose that it's time to close this session. So thanks once again. All the best for your future year in the Department of Civil Engineering. And so now we have something outside of the session. Thank you very much.